All right. Oh, fix my hair a little bit. So, this is Wednesday's lecture, second half of the chapter on statistical models and probability. Um, the Monday's lecture was a little short. This one might be a bit longer than 50 minutes, but let's just get into it. Okay, so we're looking at the process of selecting a sample from a population. Um, so in order to do that, we need to look at probability models, which are structurally very similar to the statistical models that we've been looking at. Um, so suppose that our jar, again, we're back to our jar of marbles, right? Contains 200 marbles, 4 different colors. So we've got red, green, blue, and yellow. On the right here is a chart of the proportions to the amounts of different colors and different sizes of marbles, right? So there's 100 red out of 200 of the red, right? 50 are large, 50 are small, and so on down the chart. One sort of terminological thing in a probability model, we talk about random variables instead of just variables. So here we have 2 random variables, color and size, and then color has 4 values, red, green, blue, and yellow, and the variable size has 2 possible values, large and small. Still, when we're talking about random variables and we're a probability model, values still need to be exhaustive and exclusive, right? So um, red, green, blue, and yellow exhaust the options of colors, right? All of the marbles are either red, green, blue, or yellow, um, and they are exclusive. You can only be red or green. You can't be both red and green. So probability is a measure associated with the values of random variables in a population, right? Um, and the measure for any one value is just equal to the proportion of members in the population to that value. So if you know, we've talked about proportions before, so if we know the proportion of red in the population, then we know the probability of red in the population, right? So here, the proportion of red marbles is 100 out of 200, right? And so that means that the probability of red in the population is 0.5, right? Half of the marbles are red, right? So your probability of getting red in the population is so the standard notation for this, and if you have any experience with probability um, at the basic level, this should be hopefully familiar, but even if this is new to you, it doesn't get too much more complicated than this. So here's the notation for saying the probability of red, right? So it's the P stands for the probability of, parentheses is the thing that it's the probability of. So your probability of red is 0.5, or in other words, right, 50% chance of getting red. That's all similar concepts that you can transpose. Okay, so you might sometimes see it written with the variable, with the value as well, right? So R is the value of the variable. You might, in the notation, also see the variable written, which is color, right? So if you saw the probability C equals R, that means the probability that the variable color has the value red. Same thing. It means the same thing. 0.5. Okay, so that's right, the basic idea. So here's a few operations that you can do with these probabilities. So maybe you want to know the probability of a member of the population exhibiting either of 2 or even more values of random variables. So for example, right, maybe I want to know the probability that a marble is either red or green, right? Um, well, if there's 100 red marbles, right, in the jar, and there's 50 green marbles in the jar. Um, that means 150 are either red or green, right? So that means that the proportion of red or green in the population is 150, 100, right? So divide 150 by 200, you get 0.75. So the probability of red or green in the population is 0.75. Um, So that seems like maybe we're just adding the probabilities together, right? So the probability of red, 0.5, the probability of green, right? 50 out of 200 is 0.25. So you add those together, you get 0.75. Um, yes, but be careful, right? So here's why. If we try it with a slightly different situation, right? So suppose you wanted to know the probability that a marble is red or large. Um, well, probability of red is still 0.5, right? 100 out of the 200 are red. And the probability of large is also 0.5. So this is not explicit. If you look on the size column, right, you have to add up all the large marbles, but it'll add up to 100 marbles. So that means that, again, half of the marbles are large. So that's also 0.5. Um, if we just tried to add up those probabilities, that would add up to 1. It would basically be saying all of the marbles are either red or large. Um, but that's not true because we've got some small green marbles, we've got some small blue marbles, we've got some small yellow marbles. Those marbles are neither red nor large. So why? What went wrong in that calculation? Well, the problem there is that color and size are not exclusive values, right? A marble can be both red and large. So what we did there by just adding up those probabilities is we counted some of the marbles twice. So the addition rule, like the simple version of the addition rule that we saw in the previous slide, only works for exclusive values of random variables. So um, a marble is either red or green, right? Those values are exclusive. And in that case, you can just add up the probabilities, the probability of either red or green. But when they're not exclusive, like color and size, then you can't use that simple version of the rule. Um, you're going to have to use a slightly more complicated version, right? So for now, we have an equation that says the probability of A or B is the probability of A plus the probability of B when A and B are exclusive values of a random variable. You might also write another rule, another operation you might want to do on these probabilities is you might want to know uh, the probability that a member of the population will exhibit some combination of values of random variables, right? You might want to know the probability that a marble is both red and large, right? Okay, well, let's look at the table. Um, we can see that 50 of the 200 marbles are both red and large, right? It's right there on the top line. So the probability of red and large is 0.25, 50 out of 200. Divide that, that'll give you 0.25. That might suggest to you that all you really need to do is multiply the probability of red, which is 0.5, times the probability of large, which is also 0.5. Remember, right? If we add up all the large marbles in the column, we get 100 out of 200. Well, 0.5 times 0.5 is 0.25. So is that all we need to do? Sort of, right? In certain cases. Again, like the simple addition rule, um, there is a simple multiplication rule, but it only holds under certain circumstances. For example, right, here's a figure with a different sort of distribution of marbles and sizes, right? Here we have um, 80 large red marbles, right, instead of 50. Um, so that's 0.4, right, um, is the probability of a marble being large and red, right? 80 out of 200. Divide 80 by 200, that's 0.4. But here still, the probability of red is 0.5. We still have 100 out of 200 red marbles. And if you add up the larges, you still get 100 large marbles. So the probability of large is still 0.5. If we multiplied those together, we get 0.25, but we can see from the chart that the actual answer is 0.4, right? 80 out of 200. Okay, so what went wrong in this situation? Well, in the previous slide, the variables of color and size were not correlated, right? And remember that by correlation, we just mean there is perfectly equal numbers of large and small for each color. There were no more large, right, red marbles than there were. It, sorry, to be specific, it's not that there were sort of more, but it's the percentage, right? So there wasn't a greater percentage of red larges, then there was a percentage of green larges, right, and so on. But on this chart that we're looking at now, there is a correlation, right? 80% of the reds are large, right? Whereas 20% of the greens are large, right? So now seems like red and largeness are going together. So that's what we mean to say red and large are correlated on this chart. They weren't on the previous chart. And in those cases, the simple multiplication does not work, right? So what we can say is the probability of A and B equals the probability of A times the probability of B when the values of A and B are random variables that are not correlated. So again, these were our sort of two different models, right? So we switched in that last one to model 2. Previously, we had reds, we had non-reds, right? Half of the reds were large, half of the non-reds were large. In model 2, we switched to 80% of the reds being large, 20% of the non-reds being large. And in that case, we can't, in the model 2 version, we can't do the simple multiplication rule. And in the model 1 version. Because model 1 is no correlation. Model 2, we've got a correlation between redness and largeness. Okay, one more concept. Now, again, these may be review for you if you've already dealt with probabilities, probability theory. If this is new to you, we're just sort of like front loading sort of a bunch of concepts and terminology and stuff. So, take it slow. Consult the book, go back and make sure that you're sort of getting this because it all builds on each other. If I'm sure you've had taken sort of mathy classes before or logic, something like that, and you really want to make sure you're getting every step because you miss one thing and it kind of snowballs on you. Right? So try to take it easy, but that's just sort of the nature of the beast. Okay, so conditional probabilities, right? Another concept that we might want to use here. So another way to think about the probability that a marble is both red and large, right? This multiplication rule. You might think about it in terms of conditional properties, right? So think about picking a marble as like a two-stage process. So you pick out the red marbles, right? And then you search among those reds for the large ones. We can say the probability of a marble's being large given that it is red, right? You picked out all the reds, and then given that we're dealing only with red marbles, what's the probability of getting a large, right? So you'll symbolize that. That's called a conditional probability, and you'd symbolize it as this, right? P, the probability of L/R. So probability of being large given that it's red, right, is how you would say that. Slash means given that, right? So, or probability of large conditional on red. So it means kind of the second half goes first when you're thinking about it conceptually. L/R means I've picked out all the reds. Now among these reds, which ones are large? Okay, so with the concept of a conditional probability, we can now define a more general multiplication rule for probability. We're still in model 2 here, you'll see on the right, where we've got 100 reds and then 80 of those are large. So we have a correlation here in the population between redness and largeness, right? So if A and B are values of two random variables, then the probability of A and B is the probability of A times the probability of B given A, right? Or we can say times the probability of B conditional on A, right? Now, if the variables are not correlated, the probability of B conditional on A just is the probability of B. And that's why we get the simple multiplication rule in cases where there isn't correlations, right? And that'll give us the correct answer for the previous problem, where it was 50 large reds, right? But here we can also use the more general calculation, right, and run that number. So the probability of red and large here in this population where there is a correlation is the probability of A, so that's red, probability of red times the probability of the marble being large given that it's red. And we can look at the chart to figure that conditional probability. So out of the red marbles, 80 are large, right? We see that right in the second column. So that's right, 80 out of 100, 0.8, right? If you, again, convince yourself, divide 80 by 100 in your calculator, you'll get 0.8. All right, so we have probability of R 0.5 times the probability of L conditional on R 0.8, multiply those together, then you get 0.4. That's the right answer, right? Okay, so we can also produce a general addition rule, right, given this concept. So if A and B are two values of random variables, then the probability of A or B will be equal to the probability of A plus the probability of B minus the probability of A and B, right? So here, remember the problem sometimes with the simple addition rule is you can overcount, right? Here we're subtracting out the overcounting, subtracting out the probability of A and B, right? So back in the previous slide, right, we get that the probability of large or red is the probability of large plus the probability of red minus the probability of large and red. So that's 0.5 plus 0.5 minus 0.25 equals 0.75, right? If the variables are exclusive, then the probability of A and B will equal 0. And that's why simple addition rule, right? When A and B equals 0, then that minus just becomes minus. Okay, so those concepts out of the way. If that was a little fast for you, I recommend going back through the text and convincing yourself that all that makes sense. Um, I warn you against just sort of like letting it slide by and thinking, maybe I don't need it, right? Yeah, you'll need it. Okay. Okay, so here's a little problem, introduces to the sampling process and using some of these um, techniques that we've just learned. So imagine a jury consisting of 3 judges. So the first 2 judges they've been around a while and they've sort of looked back at their past performance and they know that the probability of their coming to a correct decision in any given case is 3 out of 4. What that means is sort of 3/4 of the time when they conclude that a defendant is guilty or not guilty, he actually is guilty, right? They get it right or not guilty, right? Um, the other quarter of the time, they end up getting it wrong, right? They say he's guilty when it turns out he's not, or vice versa. Okay, so that's the 2 judges. They got a 0.75 batting average, right? They get it right 3/4 of the time. The third judge is sort of secretly irresponsible and doesn't even try to get it right. He just kind of goes under his robe and flips a coin. If it's head, he says guilty, tails not guilty, right? So he's got a 0.5 probability of getting it right, same as the coin. So we've got these 3 judges, and when they're working together, their verdict is decided by a simple majority, right? What do the 2 out of 3 say? If 2 say guilty, 1 says not guilty, guilty, right? If all 3 say guilty, it's guilty. We want to know what's the probability that these judges will reach a correct. Right? So here's the first judge, 3/4 of the time. The probability that the first judge is correct, 3 out of 4. Second judge, for any given case, the probability that she's correct, 3 out of 4. And then for the third judge, you can't, I think my head's over, but it's 1/2. Okay, so again, what's the probability they'll yield a correct judgment in a given case? Well, there are 4 types of combinations of judgments that could yield a correct judgment. So if all 3 are correct, they'll give us the correct verdict. But remember, it's just a simple majority, so only 2 of them need to be correct for us to get the correct judgment, right? So maybe for Judge 1 and Judge 2 get it right, but Judge 3 gets it wrong, right? Maybe Judge 1 gets it right, Judge 2 gets it wrong, and Judge 3 gets it right, right? Or it could be the Judge 1 gets it wrong and the other 2 get it right. That's in the chart over there. Those are the 4 ways we could get a correct judgment. Now we can calculate the probability of each of those outcomes, right? So the combinations are mutually exclusive, right? So once we have the probability of each of those 4, then we can apply the simple addition rule to determine the overall probability. So, in other words, the probability of correct verdict one, right? The probability of getting a correct, all three correct, plus the probability of getting the first two correct, with the third one wrong, and so on down this chart. You just add up those probabilities, right? These are mutually exclusive, right? You can't have, there's only one set of judgments, right? They don't then do it again or something. They don't do it mutually exclusive. Okay, so the question is, so that'll be simple addition, right? That's not a big problem. The question is, for each line, how do we calculate the probability of that happening, right? Fortunately, we can use the simple multiplication rule because any particular, the first judge's judgment is not correlated with the second or the third, right? They're all making the judgment independently. So we know that judge one will be correct three-quarters of the time, right? The probability of a correct verdict from judge one will be 0.75, and that'll be that way every time. It has nothing to do with what the other two judges do. So those outcomes are not correlated, so we can use the simple multiplication rule. Okay, so we can just calculate that up. You see on the bottom there. So the probability that all three are correct is the probability that the first one is correct times the probability that the second one is correct times the probability that the third one is correct. And that'll be 3/4 times 3/4 times 1/2, or 9/32, right? And it turns out that in every case, right, it will be, you'll get the same answer. You don't get the same answer in every case, right? So the first two cases you get the same answer. Now look at line 3. We have the first one correct, right? So for the third judge, who's the flippant judge, you'll notice that the probability is 1/2 every single time, right? That's because they're flipping the coin. So it's only the first two judges where the probabilities change. So you'll notice on line 3, right? On that scenario, the second one gets it wrong, right? So since the probability of them getting it right is 0.75, the probability of them getting it wrong is 0.25, or 1/4, right? So in the third situation, you have the first one getting it right, 3/4 probability of that. The second one gets it wrong, which is a 1/4 probability, and then the flippant judge is always 1/2. So in that case, you get a 3/32, and then on the fourth line, the probabilities are switched. So that time, the first judge gets it wrong, and there's a 0.25 or 1/4 probability that they'll get it wrong, and then the second one getting it right, and the third one getting it right, but it's the same probability as the third one getting it wrong, right? Okay, so we've calculated 4 probabilities, and then we can add them all up, right? And you should end up with a probability of not 1/4. Hold on, let me pause this. Yeah, I just had to double check with the calculator to yeah, that's a misprint. Should be a probability of 3/4. So I'll fix that on the slides when I upload them. So yeah, you add up those 9/32 plus 9/32 plus 3/32 plus 3/32 will give you 0.75 or 3/4. Okay, so that was just a little practice with right, adding up probabilities, right, simple addition, simple multiplication, and kind of knowing when you can use simple addition, simple multiplication. So on to sampling, right? So we're about not quite halfway through the lecture. Maybe we'll get in under 50 minutes. I don't know. I don't want to rush myself here. I feel like I'm forcing myself to rush. I know this stuff can be tough, but fortunately this is recorded, right? You've got the lecture slides, you've got the book. Play this back again, slow it down, whatever you need. Come to office hours, send me an email, go to discussion, right? Now's the time to feel free to utilize all those resources, right? If you don't read the book and only watch this video while also staring at your phone and then sort of zone out during discussion, I really worry that people are going to fall behind on this because, okay. So, on to this concept of sampling. So, 2 types of sampling that you want to know, or at least make the distinction. sampling with replacement, sampling without replacement. So what does that mean? So back to our marbles in the jar, right? Uh, what happens if we sample marbles in the jar without replacement? What that means is like we pull a marble out, oh, it's red, and we set it aside, right? Well, what that means is now when we make our second draw, there's one less red marble in the jar, and all of a sudden the proportion of red marbles in the jar has changed. So the probability that the next marble will be red has changed, right? Now it's 49 out of 99 instead of, oh, sorry. So it was 100, right, red marbles in a 200 marble jar. Now, after I pulled the first time I pull, probability is 100 out of 200, right? Or zero point 0.5. I'll pull a red marble. Well, now there's one marble gone. So now we've got 99 red marbles in a 199 marble jar. And I can't do that math in my head, but it's a different probability than it was before. Slightly lower probability of getting red. That's sampling without replacement, right? Every time you sample, it changes, right, the probability. Whereas sampling with replacement, right, we pull the marble from the jar, oh, it's red, throw it back in, whatever, shake up the jar, right? So next pull, exact same probabilities because the exact same marbles in the jar. That's sampling with replacement, much simpler, right, calculations, as you can see. So for our purposes, we're just always going to assume that we're dealing with sampling with replacement, right? It's too complicated to worry about the population changing constantly. Um, and it sort of translates even to real world samples where you're actually not doing replacement, but the population is so big, right? And the sample size is so big that like it doesn't really matter, right? So if I'm sampling out of like the US male population, right, of like whatever, 150 million people, and I pull one male out and set him aside, it technically changes the probabilities of the right the next draw, but the change is so infinitesimal that it's for all practical purposes we can treat it like sampling with replacement. Okay, so a little terminology. So that act of pulling a marble out of a jar, right, choosing an individual from a population, choosing a male from the male population of the U.S. That's called a trial, right? So um, a, a single trial is a sample. It's a sample of one, right? Um, let's do let's deal with the smallest sample that's like more than one. That would be two trials, right? Let's start there. Of course, such a small sample would not tell us much about whatever population we're drawing from, but it does help us um, concept of sampling. So we're going to start there and then we're going to build up. So let's use our jar, 200 marbles, and we're going to do some sampling with replacement. So we'll say the variable of interest is color, and we're only going to consider two values, red and non-red. Keep it as simple as possible. So sampling is just a sequence of trials, right? Again, the trial is just picking an individual out of the jar. Um, each trial is a selection of one member from the population. So we can represent each trial with a different variable. So call them x1, x2, x3 on to xn, depending on how many trials you do, right? And in our example, each variable, right, has two possible values, R for red and for non-red, right? So two trials would be represented as, right, a series x1, x2. So in our case, there'd be four possible results of selecting two marbles from the population. You can pull an R and then pull another R, right? That's one set of two trials. Um, you could pull an R and a non-red, right? That would be another possible set of trials, and so on. You could pull a non-red and a red, or you could pull two non-reds, right? And every set of trials will be one of those four, the only possibility. Now let's imagine like a large set of outcomes of these two trials as sort of a population in itself. It's not a population of marbles, but it's like a population of sequences of marble selection, right? So um, suppose we only perform one trial, right, of X1, X2, and it's RR, or whatever it ends up being, but there's also a huge set of possible trials if you kept going for on and on and on. Now, each one of those, 2, 3, or 4, and so on, each one of those would end up being one of those four possible ones. It would be an RR or an NN or an RN or something like that. But you can imagine doing as many trials as you like, right? So many that it starts to look like a population in and of itself. So we can talk about probabilities or frequencies in that sort of imaginary population of trials, right? If I do if I do these sets of two over and over and over, what sort of trends will I see? Okay, well, with that idea of like the imaginary sort of like long series of picking two marbles over and over, we can start talking about what it means for sampling to be random. So for sampling to be random, two things must be true. First of all, on each trial, the probability of red must be the probability of red in the population, right? So in our jar, we happen to know that there are 100 red marbles out of 200 total marbles, right? So the probability is 0.5. Well, on each trial, that should be the actual probability of pulling a red marble, right? And it is in our example, right? Um, so if we think about our imaginary large set of many trials, right, over the long term, we should see that half of the first trials in the set are R's, right? All the X1s, half of those should be R's, and half of them half of the X2s should also be R's, right? That's what it means for the probability of picking an R to be 0.5, right? Over the long term, half of them are in fact R's, right? Second condition on for something to qualify as random sampling is that there must be no correlation between the outcomes of the two trials, right? So, right, if I pull an R in the first trial, that should have no effect on the probability of pulling an R on the second trial. It should be no greater or less than the probability. So what does that mean, cashed out in terms of our large imaginary set of trials? It means that of all the trials that have an R, of all the sets, right, that have an R for X1 for the first trial, 50% of those should have an R in the second trial, right? There's no correlation. Half of them turn out red, half of them turn out non-red. Again, over the long term. So what does this mean, right? This means randomness is not a property of the population at all, right? Maybe for all we know, there is a correlation, right, between different variables or different values of variables in the population. What we're saying, right, and what we're saying there shouldn't be a correlation between is sort of the sampling process, right? We're concerned with the sets of possible outcomes. There shouldn't be correlations in those. Um, so, for example, right now we have sort of 100 reds and 100 non-reds in a 200 marble jar, right? But um, you could run the random sampling, all these conditions of random sampling would be exactly the same if we were dealing with greens and non-greens, which is here we've got 25% greens and 75% non-greens. So none of this depends on the proportion of red and non-red being equal in any way in the jar, right? Again, we're talking about the process. Okay. Okay, time to take the attendance quiz. Giving you a moment if you're typing this in real time. And we will move on now. Okay, so we can calculate the probability, right, of some result, right? So if you want to know the probability of getting R on both trials, right? Well, that'll be the probability that x1 equals R and the probability that x1 equals R and x2 equals R, which will be the probability of x1 equals R times the probability of x2 equals R, right? Again, we know there's no correlation, so we can use simple multiplication rule. So we get 0.5 times 0.5, which is 0.25. So the probability of RR as an outcome is 0.25. Right? We could try it for green, right? What's the probability of green? Um, well, on any given trial, the probability is 0.25, so we can just, again, multiply them up. You get 1/16. Probability of green, non-green would be 0.25 times 0.75, so you get 0.1875 or 3/16. Right? So again, calculating the probability of a given set, right, of two trials is just a matter of, uh, because it's random sampling and they're not correlated, it's just a matter of multiplying up the probabilities of each individual trial. Okay, on to the concept of relative frequency. So far we've been distinguishing the outcome Rn from Nr, right? But most of the time we're actually not going to be interested in the order that much, right? We instead only really care about the relative frequency of types of income or outcomes, sorry. And in terms of relative frequency, we can treat Rn and Nr as the same outcome, right? Um, Meaning that in both of those sets, the relative frequency of red marbles is 0.5, right? In the Rn set, right, it's half Rs. In the Nr set, it's half Rs, right? So the relative frequency there is 0.5. So in terms of relative frequencies of red marbles, right, instead of 4 different outcomes, we actually only have 3, where none of the 2 trials in the set brings up a red marble, where only one of them, right, brings up a red marble, or where both of them are red marbles. So let's use the variable y to represent these different outcomes, right? These 3 possible outcomes here of different relative frequencies of reds. So if you want to calculate py, right, the probability of each of these relative frequencies of reds, it's pretty easy to calculate, as there's only one way each can happen, right? So the probability of 0 Rs, or sorry, so the probability of 2 of those outcomes are really easy to calculate. So the 0 reds, right, and the all reds can only happen one way, right? There's only one out of the earlier set of 4 that are those. So the probability of 0 Rs is the same as the probability of non-red, which is 0.25, right? 0.5 times 0.5. And likewise, the probability of getting 2 reds is, as we've seen, 0.5 times 0.5 or 0.25. So those we can figure out. So a slightly more complicated question is, what is the probability of y? Again, what is the probability of getting the relative frequency of R's being 0.5? Which is to say, what's the probability of getting, right, a red in one of the 2 trials, right? Which is to say, what's the probability of getting either red and then non-red, or getting non-red and then red, right? Those are the 2 ways we can get a relative frequency of 0.5 reds, right? And for this, we can use the simple addition rule. So, because again, those are, right, exclusive outcomes. So the probability of getting 1R, right, equals the probability of getting the sequence Rn or getting the sequence Nr, and that equals the probability, just the addition, right, the sum of the probability of Rn and the probability of Nr, which is 1/4 plus 1/4, 1/2, right? So these 3 probabilities form what we call a probability distribution for the relative frequency of 0.5, sorry, for the relative frequencies of random selections from a model population, right? So this is what we call a sampling distribution. It'll be on the next. So this is our probability distribution in our 2 trial sample, right? So the most probable outcome is getting half reds, right? There's a 0.5 probability of getting that outcome. Less likely are getting 0 reds, right? There's a 0.25 probability of that outcome over on the left, and getting 1 red, right? And that, right. So getting a 0.5 reds or getting all reds. So 1 means all reds, right? It's like a probability of 1, and the other is sort of a relative frequency of 1 and a relative frequency of 0. So the y-axis there is the probability, and then the x-axis here is the relative frequency, right? So saying it all again, probability of getting a relative frequency of 0.5 Rs is 0.5, right? The probability of getting a relative frequency of 0 Rs is 5, and the probability of getting a relative frequency of Rs, which is 1, meaning all Rs, is 0.25. Okay, so hopefully that made sense. Now moving on to 3 trials. So what if we did 3 trials without replacement from the same population? Here we've got a sequence of random variables, here x1, x2, x3. Each random variable can again take the value r or n. So now we've got, instead of 4, we've got 8 different mutually exclusive, right, possible results, right? You could have RRR, RRN, RNR, and so on, right? So getting more complicated but once again, let's imagine a large set of such samples, right? So the sampling is random. Then half of these triplets will have an R in the first trial, right? Half will have an R in the second trial. Half will have an R in the third trial. So the probability of, right, x1 being an R is equal to the probability of x2 being an R, which is equal to the probability of x3 being an R, which is, right? And the results are not correlated, right? So we have random sampling. So to calculate the probability of the result, red, 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 right? Red on each trial of the 3. You can use simple multiplication. So that'll be the probability that our first pull is red times the probability that our second pull is red times the probability that our third pull is red. Each pull, the probability is 0.5, right? Because that's, again, that's the proportion of reds in the population, half of them. So it's the probability of getting a red all 3 times, 0.5 times 0.5 times 0.5, so that's 0.125. And then you can calculate the probabilities of all the other outcomes as well, right? So the random variable y has 4 different possible variables. So out of the 8, right, many of them are going to have the same relative frequency of reds, right? For example, there's 3 ways to get 1 red, right? It could be an RNN, it could be an NRN, it could be NNR. So the probability of getting 1 R will be the sum of each of the probabilities. So each of them is 0.125, right? So the probability of getting 1 R of a relative frequency of 1 R out of 3 is 0.375. Do, once again, calculate the probabilities just as we did for 2 trials of each of the 4 possible relative frequencies of R's, and you end up with a different sampling distribution here, right? So in the center now, we have getting 1 R is 0.33 Rs, right? That's a relative frequency of like, right, 1/3 Rs. You got a 0.375 probability of getting that. That's the thing we just calculated. The probability of getting 2 Rs out of 3 will be, right, which is a 0.67 relative frequency of Rs, right? 2 of the 3. The probability of getting that is also 0.375. We didn't explicitly calculate that, but you can do that yourself if you want. And then the probability of getting no Rs or of getting all Rs is 0.125 on either end of the distribution. And we can keep ramping it up, right? We're still dealing with very small samples, right? But we're seeing a trend, right? What happens is your samples get larger and larger through this probability distribution. Um, so you do 4 or 5 trials, you'd be looking at 16 and 32 different possible sequences. So we're not going to sort of run the math here, right? But you're going to get sampling distributions that look like the next slide, right? Which I'll show you in a moment. So again, even a sample of 4 or 5 is still going to be too small to do really anything useful in forming a statistical hypothesis, but it's helping us flesh out this concept. And even bigger samples, you couldn't even sort of do the calculations by hand, or at least it would take you a very long time. Um, but in principle, right, of what's going on, there's no difference between a sample of 2 and a sample of 500, right? It's just same process, same math, just bigger, more ungainly calculations. So let's look at some more sampling distributions and what happens as the sample gets bigger and bigger. So here we have 4 trials on the left, right? So you'll notice that um, the probability of getting 0.5 Rs, so 2 out of 4 reds, is 0.375. And then you've got on either side of it, the probability of getting 1 out of 4 reds is 0.25. The probability of getting 3 out of 4 reds is 0.25. And the probability of getting no reds or all reds is 0.062. So we're getting more possibilities, more spread out, and the probability of each particular outcome, you notice, is all going down, right? Um, so with 5 trials, right, 0.4 and 0.6 relative frequency of Rs, 0.312. Now the probability of getting no Rs is down to 0.031. Let's look at some even bigger samples, right? So the next slides are going to show us samples of 10, 20, 50 trials, and then 100, 250, 500 trials. And we're going to notice some trends as the samples get larger. So first of all, the most probable sample frequency, right, the peak of the distribution, is going to agree with the ratio of red marbles in the population, which has never changed, right? We're still dealing with the same jar. We're just pulling more marbles out of it, right? Well, yeah. We were talking about a 200 marble jar, and as the sample size goes up to 500, maybe you're dealing with a bigger jar. But like at any rate, the proportion is the same, right? 0.5, half red marbles, right? In all these situations. So doesn't matter as the sample gets larger, the most likely outcome is still going to be 0.5, right? We call that either the average or the mean frequency or the expected frequency. Right? The relative frequency is the one sort of in the middle with the highest probability. Um, but we'll also notice that the probability of that most probable outcome coming down as the sample gets larger, right? So with a sample of 2, the probability of getting 1 out of 2 being red was 50%. We get up to a sample of 10, you got a 25% chance of getting 5 out of 10 reds. And then with a sample of 100, you only have an 8% chance of getting 50 out of 100, right? Sample of 250, you've got a 5% chance of getting 125 out of 250. Let's look at the right. So we got a 10 trial, right? So many more possibilities. Again, 0.5, right, is the tallest line right in the middle. So the most probable outcome, but we only have a probability of 0.25 of actually getting that outcome. And then we see, right, 25 trials and then 50 trials. And then, as we said, 0.5 is still the longest line, the tallest line in the middle, but the probability of getting that drops to like 0.15 and then down to about 0.1. Now we're at 100 trials, 250 trials, and 500 trials, right? So we're noticing, right, that the range of the outcomes are kind of clustering in a little bit. Everything's right. You have more possible outcomes, but the probability of getting any one outcome is getting lower and lower, right? And now we have blow-ups of 100, 250, and 500 here. So you can examine those and convince yourself that the trends I'm talking about are true. All right, so seeing this trend, right, of what happens as we take larger and larger samples can help us get into this concept of standard deviation. So even though um, the zero point 0.5 is still the most probable sample frequency, right? So again, even if I pull 100 marbles, um, the most likely outcome is to get 50 out of 100. Um, that probability is going to go down because there's so many other possibilities, right? I could also get 49, right? I could also get 25, I could get 23, I get 22. There's lots of possibilities, so it makes sense that even though it's the most probable of a lot of sort of improbable outcomes, because any one is sort of improbable that you'll get it, because the 1 in 100 shot, you'll get exactly that combination of reds, right? Um, Not exactly a 1 in 100 shot, right? We're dealing with relative frequencies. But at any rate, the odds that you'll get exactly 50 is getting pretty low as the sample gets larger, right? Out of 100, right? But you can expect that you're likely to get pretty close to that, right? Um, so what does that mean to say, no, it's pretty likely that I'll get close to 50 if I'm sampling 100, or it's pretty likely that I'll get close to 150 if I'm sampling 300, right? What does this pretty close to intuition mean? Is there a more rigorous way to define that? And that essentially is the notion of standard deviation, right? So consider the sampling distribution, and we're over 50 minutes now. I apologize, but I got 4 more slides, right? Um, right. So the distribution for relative frequencies in 100 trials, right, from a population with 50% of its members exhibiting the property of interest. So the expected number is 50, right, in 100 trials, but the probability of getting exactly 50 is only 0.08. However, the probability of getting somewhere between 46 and 54 is 67%. Now that's a much more healthy probability. That says, right, I pull 100 marbles out of my jar, 67% chance that I'm going to get either 46 reds or 47 reds or 48 or 49 or 50 or 51 or 52 or 53 or 54, right? Those are the most likely outcomes. And in fact, you add them together and you got a 67% chance you're going to get one of those outcomes. We call that 67% chance mark one standard deviation of the mean, right? In this course, we're not going to talk about how those numbers are arrived at, but that's just what it is, right? So if you spread it out a bit more, right? So the probability of getting like a 0.46 relative frequency of reds to a zero point 0.6 relative frequency of reds when the actual right proportion is 0.5, you got a 95% chance that if you pull 100 marbles, you're going to get between 40 and 60 reds, right? Um, that's 2 standard deviations of the mean. Gives you 95% probability that you're right? The relative frequency you see is going to come in that range. And then 3 standard deviations would give you 99% probability. We're going to be focusing a lot on this 95%, this 2 standard deviation. Um, so standard deviation is independent of sample size, right? If the sample was 200, right, 1 standard deviation is still going to mean the area around the mean, the values centered around the mean, where 67% of the outcome will lie, right? 2 standard deviations will mean what's the range, right, within 95% of the outcomes will lie. Right? So again, here's a chart with standard deviation, right? So 1 standard deviation either side of the mean. So the line in the center is the mean, right? That's still the most likely outcome, but again, when you're dealing with a large sample, the odds of getting that actual outcome are low, but you've got a pretty good chance, 67% chance, that your outcome is going to be within 1 standard deviation either side of that, 95% chance that your outcome, right, will be within 2 standard deviations, and then 99% chance within 3. So we can see from the previous figures that a larger sample is going to increase the probability of getting a relative number of R's that are pretty near the ratio of R's in the actual population, right? So again, if the actual ratio is 0.5, right, half of the population are R's, well, if I just draw 2, I got a pretty good chance of getting like 0.25, right, of getting like no R's, right, which is like way off from the population, right? I've got like a 25% chance of getting no R's in trials of 2. Where a trial of 100, like the odds of getting no R's are tiny, right? And I got a pretty good chance of whatever my outcome is going to be pretty close to 0.5, right? Maybe it'll be 0.45 or right 0.55, but it's going to be close. Um, so that's the idea, anyways, right? We can see why getting a large sample guarantees or almost guarantees gives you a much higher probability that the proportion of R's you find in your sample will be similar to the proportion of the R's in the population. Okay, so our main example, right, so far has been with equal probabilities for R and N, right? Each was 0.5. And this was largely done for the sake of simplicity, simpler calculations. Um, But if you have different probabilities, if it was like 3/4 R's and 25% non-reds, like nothing fundamental would change, right? So in the next figure, you'll see a situation of if we applied it to green marbles, right? Where it's like 25% green, 3/4 non-green, um, you'll see the same tendencies, right? It's just the whole thing is sort of shifted, right? And the tails um, get a little funky. You'll see it'll look a little asymmetric, but it's basically the same. Right. So this is what it looks when you don't quite have a 50-50, right? Here we've got the 75-25, but similar trends, right, from 25 trials to 50 trials. For our purposes, um, not a big difference, right? Okay. We came in at 56 minutes. Not too bad considering uh, I went real short. I think the last lecture was closer to 30, so I think we're on track for still keeping you under 100 minutes for the week, right? So I will stop it here. And yes, please, if you got lost anywhere, rewind, watch it again, go back to the textbook, right? Um, this is a part where you really kind of need to keep up because it's building on stuff that you're learning. Okay. All right. Have a good week.